Yeah, good afternoon all. Hope I'm audible. I'm Nandeesh and I'm here to present my work on geometry control of short-line match casting using computational BIM. First of all, short-line match casting is a process which is employed at the casting yard to produce segmental bridges in a controlled manner. So looking at the animation there, you understand the process that any segment cast is cast between a fixed support and the previously cast segment in order to get the precise geometry. So as you can see, this is a localized method of casting segments, and it is complicated. Though it has advantages like it consumes very less space, and it has higher pliability for finer adjustments which you can make. It is complex with respect to the geometry. Uh, Firstly, because you have the coordinate system changing for each of these segments, because the origin or the frame of reference for the surveyor is at the fixed support, which you can see there. Whereas each segment keeps moving and has to change the coordinate system for each system. And in addition to that, you have errors which creep into the system, such as misalignment, human error, and vibrations due to the concreting process, which will add on and increase the complexity of the problem. So this becomes very critical because when you don't address this geometry control problem, and if there is error of even few millimeters, it can deviate the bridge when erected over several meters. So the current method deployed or the workflow deployed to control the geometry is that the global coordinates of the bridge is provided by the designer in terms of the coordinates, which is in Excel format of each of these edges in terms of global coordinates. And then after that, the global coordinates is then run through a software called as MC3D, which converts the global coordinates to the local coordinates at the casting yard. It is then handed over to the surveyor at site, who then goes out with its instrument and sets out the coordinates which he wants through this setup, which is available at site. And then after the setting up is done by adjusting these jacks at the bottom in order to get the required geometry, the concreting is done for the as planned geometry. Subsequent to the casting, there can be some errors which have creeped into the system. So in order to capture the as-cast data, the surveyor again goes back and collects the data of the already cast segments, which is then fed back to the software, which again computes the error and gives out the corrected coordinates. So as you can see from the images earlier, that the workflow which I mentioned involves a lot of office work and has a lot of manual intervention. And the software which I showed some snapshots were of really of not of this latest era of BIM. It is quite outdated and is also costly to procure. So in this regard, my objectives are aligned to developing a custom software and also an algorithm to correct the geometric errors which occur in the system, and to integrate that with the BIM workflow, which will be making the process more efficient in terms of geometric control. So just diving deeper into the concept of how the errors are corrected. Assuming that error, so this is a plan view of our bridge. So S1, Sn-1 represents the segment in the plan view. And suppose there is an error which is creeped into the system. Instead of PE, if there is a deviation at PE dash, it has to be compensated. We have two strategies to compensate this. Either you do a single step error minimization, or you do a more gradual error minimization. As you can see, and it is more obvious to have a more gradual error minimization, which is appropriate, because it will uphold the constraints of formwork. For example, the width of the formwork is abided by, and also the alignment constraints. For example, the width of the roadway, the constraints such as the crinks are not formed in the final right of way is ensured by having a more gradual compensation. So diving a little deeper into how it is mathematically modeled. So we set up a set of relationship, in a trilateral relationship, which consider distance between critical points in the network. So the critical points which we choose here is the first point of the bridge, which is lying on the pier, and the last point, because in between the spans, in between the two piers, is the bridge is independent, but it has to ultimately go and support on these two supports. So that becomes a very critical constraint here. And apart from that, the points which are on the edge of the previous segment and the succeeding segment are also few of the critical points. So when you set up this relationship, and when there are errors which have creeped in, and when you try to solve this, you don't get a unique solution. You get it will be an over-determined system where you get multiple solution which is spread across a region or a boundary. And in order to get the best fit out of this region, you can apply a least square method, which will give you the minimized error of this the error which is generated. So mathematically, it is again formulated in terms of matrix operations. Due to paucity of time, I'll just skip to and go through the software tool which is developed. So this tool is called GEMBS BSC. So it has 4 modules which is integrated with BIM. So it is basically running on Revit and Dynamo. So the first module pulls up the coordinates from the BIM model automatically, and then goes to the second module where the first segment of the bridge is converted to the local coordinates and provided to the surveyor. The next one runs for the typical segments, which is on the error correction algorithm. And the last one is a ASCII data generator, which is for the database. And in all these 4 modules is always being coordinated with the site activities. So let me take you deeper into each of these modules. So when you look at the first module, which is the coordinate exporter module, so once you have the BIM model in place, and you run this algorithm in Dynamo, which is the and Dynamo player, which is the UI you can see here. So you get the global coordinates of the BIM model at key control points. So the control points in any segmental bridge is on the 4 corners and 2 in the midpoint of the edges. So after the first module is completed, you go on to the starter segment setup, which is the first segment of the span. So there you have to make a conversion from the global coordinate to the local coordinate at the casting head. So as you can see the output here, so it gives the local coordinates. Subsequently, the main part or the algorithm part comes in here, wherein the software or the tool takes in the local coordinates of the previous cast segment, converts it back to the local global coordinates in order to see the deviations. And then subsequently, the algorithm which was explained earlier was run in the background in the Dynamo environment. And then you compute the corrected coordinates of the subsequent segment, and then give out the corrected coordinates of the subsequent segments in terms of local coordinates as an output. So this is the third step. And the fourth step is the ASCII data generator, which is a parametrically modeled method wherein you generate the ASCII data with the ASCII points. After this, the tool was successfully developed. We tried to validate it with some of the standard softwares which are available, like MC3D. So we tried to induce an error to see how our algorithm behaves with respect to how the other standard softwares behave. So when an error was introduced, our tool was gradually reducing it at the end of the span, whereas the standard software had more abruptly encountered and more abruptly tried to address the errors. And then you see that there's a residual error which was there, which is not addressed in the standard software. So moving on to the conclusions, as we stated in our objectives, the errors were compensated in the subsequent segments in a more gradual manner. The BIM-based workflow will help in reducing the cycle time because a lot of office work is reduced. So the proposed algorithm can be refined further by having more weightage factors or tuning parameters by running the validation method with several projects and several data points. Also, we have significant savings in terms of time and cost with respect to procuring the software. And actually, this the proprietary software which is used here can be completely eliminated after it is reasonably validated. And last but not the least, since you have the complete database, the checklists which are required for the surveying and for other quality control can also be integrated with this workflow. So yeah, this is about my work. Thank you.
Okay, very good. Thank you.